Oh, wait, there it is. Never mind. I was
Okay, so
wrong.
maybe I didn't record it. I
No,
thought
like
I did.
you just
Oh,
started
there it is.
recording.
Yeah, you just started. Okay, that's what I'm saying. Yes, it's there now.
Because
Thank
All
you.
right.
Okay.
it was asking, do you want to start? And then you just clicked on yes. So now it's
Yeah.
Okay,
recorded.
good. Thank you. Okay, so never mind. Okay.
But you were
I
right.
thought
You
I
were
was
right.
going crazy for a second.
For some reason,
I was like,
for some
14 was
reason, it
pretty
didn't
long.
start
I
recording.
remember that red dot. Okay, never mind. Thank you. Okay, it's on now.
So apparently, we didn't. Up to this point, we didn't record what I
Not
was
at all.
doing.
So we
But
have
I
to.
think I may have a recording of this from the years we were online the whole semester, and I recorded everything.
Yeah, that's why I remember that red dot. That's why I was
Yeah,
like, I know there's supposed to be a red dot somewhere on my screen.
right.
Okay.
So we can now find the answer over here, and okay, here's the calculation. The answer: if you multiply 9/4 Q1, Q1 being 4 microcoulombs, like we just did, uh, the answer is 9 microcoulombs. One more example that we can do here. Say we have, yeah,
Sorry, for the previous problem, you knew they were equal because they were going in opposite directions, or?
right. But we were given the fact that the electric field at the center here is 0. The net electric field at the origin is 0. That was given. What does that mean? That means the electric field due to this guy has to be in one direction, and due to this guy has to be in the other direction, which, and the total electric field is 0. So by setting this equal to that, I was able to solve that equation. Here it is, this equal to that. I was able to solve that equation for Q2. Okay. The electric field due to Q1 is given by this equation. Here it is, KQ1 over R squared, which is 2 squared. And this is KQ2 over R squared, which is 3 squared, which is 9. And therefore, by solving this equation for Q2, we find out that Q2 is 9/4 times Q1. And Q1 is given to be 4 microcoulombs. And if you multiply this by that, you get that.
Okay, thank you.
Good thing you can interrupt me if you have a question. All right, one more problem like similar to this one. So we have these charges, which have these values, and we want to find the net electric field here. Okay, right at this point. So there's 3 charges contributing vectors. We got to draw these vectors. In which direction are they? So this is a positive charge, and I'm going to draw the vector because this is positive away from it over here. So since the electric field due to that vector goes away, it's going to look something like this. This is a negative charge. The electric field is going to be like this. And this is a positive charge. So the electric field will be like that. We have to add these 3 vectors. It is a somewhat meticulous problem to do that. I mean, it's not that bad because these vectors already in component form. You don't have to find the components. The only thing you need to do is find the components of this vector, okay, and then add them to the components of these 2 vectors. This has no y component. This one has no x component, so they're already there. And now, so I got to replace this with 2 vectors, the components of that one. Now, again, the electric field is given by the same equation. E is equal to KQ over R squared, where R is 1. In this, for Q3, R is 1. For Q2, R is 1. But for Q1 here, R is not 1. It's square root of 2. Okay, that comes from Pythagorean theorem. This squared plus that squared equals that squared. Okay, so now what you got to do is calculate that. And I think I do it right over here. So the first one, E1, I calculate KQ over R squared. That's E1 due to this charge here. Now R squared here, since R is the square root of 2, R squared is just 2. So E1, that's I called 12, this one here, E1, that's this vector here. So E1, we have to find the components of E1. It turns out this angle is 45 degrees. That's because these two sides are the same. So E1 is going to be equal to, well, E1, first of all, this length of this vector is 54,000 units long, 54,000 newtons. E1x, x component of that would be 54,000 times the cosine of 45, which is 38,000. Okay. And so now we know the components of this vector. This vector is already in components, so we're going to replace this vector here with this vector. Oops. And this vector here. No, not that vector there. This vector here with that one. Okay. I have a nicer drawing, I think, over here. Not over here. Take next slide. Yeah, over here. Okay, so E1, what we're doing is we're finding the components of E1. The other ones already have components. We don't have to do that. So E1 has a Y component of 38,000, an X component of 54,000, comes from multiplying 54,000 by cosine of 45. E3 and E2 are already, they're already done. You don't have to find components. So all we got to do is add this component here and subtract this component from that one, right? Because you're adding all the Y components. And I think I have the slide for that over here. So the Y components over here add up to the Y components add up to just 38, subtracting the top minus the bottom. That's 38,000 minus 72,000. And these two got to add because they're in this direction. These two subtract. Let me go back one slide. So we're finding the three vectors that we need. The X components are going to be these two. The Y components are going to be these two. These two add up. These two subtract. 38,000 minus 72,000. That's what the next slide is. How I add this. So we're going to subtract this minus that. That's going to be vectored down. All right. And then we're going to add these two. This plus that gives you 92,000. This minus that gives you 34,000, minus 34,000. So this, in fact, is your electric field vector at this point. Okay, so I know this is a tough problem. There is when you see something that looks like this, there is a video on Blackboard of a guy doing this problem, not me. A guy doing this problem exactly step by step. So if you want to see it again, because you didn't, you can look. There's a link to it on Blackboard. So now we're going to just go off to a little bit different situation. In real life, various molecules can be modeled by what's something called a dipole field. A dipole field is like two charges here that add up to Q, for example, or something like this. They could be the same charges or opposite charges. And this is actually a model of H2O water. Let me show you this little film here.
And let's go to some point here near the top right, at which we're going to begin by asking ourselves, what is the direction of the electric field at that point? So let me first draw an arrow that is the field at that point associated with the positive charge. We're fairly near the positive charge. The positive charge is positive. The field points away from it. So I've drawn a fairly long arrow. Let me do the same thing for the negative charge. The negative charge is further away, so the field is weaker because it falls off as 1 over r squared, and because the charge, the negative charge is negative, the field points toward it. So there are two field vectors. Because the force obeys the superposition principle, I can vectorially add two forces, electric forces. I can also vectorially add two fields, and there is the net field line, and that gives me the local direction tangent to the field. Now, what I need to do is move a little ways in that direction and redo the process. And you can imagine a computer would be very good at this. I'd get bored with it very quickly. So I'm going to imagine I've moved along. Eventually, I come to another point, and you'll notice I've drawn a little curved arc in there, which indicates that the direction of the field is, in fact, changing. And then I draw a couple more vectors, one pointing away from the positive charge, one pointing toward the negative charge. They've got the right direction. They're scaled as the inverse square of the distance and so on. I find out the net field from those two. I move a little further in that direction. And now I keep repeating the process until I've moved in to make that arc-like pattern. That's part of a field line. I didn't start right on the charges, but if I started right near the charges, you can see how that arc would extend back. So let me do that. And now I have a single field line starting from the positive charge, going out in that arc-like structure and returning to the negative charge. That's what the field pattern of a dipole looks like. That's only one field line. There are infinitely many field lines. They're all over the place. And so I'm going to draw a few more just to give you a sense of what the dipole field looks like. So there's the dipole's field. I won't prove it, but the dipole field at large distances actually falls off as 1 over r cubed, faster than any point charge field because the dipole has no net charge.
So this is what we're going to look at in the next job. We're going to, first of all, do a dipole, and we're going to see why it falls off as 1 over r cubed. That which gets smaller as 1 over r cubed. So basically what a dipole is you could have two charges like he did here. They could, or you could have, they could be the same charge. That's still considered a dipole field. So let's go to, not that problem, right over here. So this is a dipole where you have two charges here. They're both negative, and we want to find out we got some information about what is the electric field like right over here at point C. There's no charge here. We did a problem like this earlier. There was a third charge here, but there's no charge here. This is point A, point B, point C. There's only two charges. And the question is, well, in which direction would the net force be? Okay. On not net force, which direction would the electric field be at this point? Well, it's not too difficult to figure that out because each one, the electric field produced by each charge is toward the charge, right? So basically, if I draw a vector this way, that's the electric field due to Q1. To do Q2, the electric field will be that way. So which direction would the net electric field be? Well, these two vectors here are going to add up to what vector? This, or this?
Is it D?
It is D is right. D is right. So there will be down. Now, if these were positive charges instead of negative, these were positive charges, nothing would change much except that everything would be in the opposite direction, and the net electric field would be straight up instead straight down. And then we're going to look at, and we'll come back to this, in what's the magnitude of the electric field. But let's not do that yet. Let's just go back. And I want to demonstrate something to you on simulation right here. So this is what I have. I have two positive charges. All right. I'm going to go up the midpoint between them, just like in that triangle that we saw. And I'm going to put up a test charge there. First of all, before I do that, this is what the electric field would look like. And you can see at the midpoint, the electric field is pretty much up, like we said, for positive charges, right? It's pretty much up. It curves sideways on the charges there. But what I'm going to do is I'm going to put a test charge right in the middle, which is over here. And there it is. There's the electric field on it. Okay, this is actually the force on due to the electric field of these two charges. Now, what would happen if I go further away? You notice it gets smaller, 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 as it should. But what if I go the other way? Well, as it should, it gets bigger, 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 until it starts getting smaller. Why would it start getting smaller? Well, once you get close, the total electric charge due to both of these is starting to cancel each other out. Okay, in fact, right over here, that the total electric charge would be 0. Well, it's not 0, but well, we'll see in a minute why it decreases and increases. Now, if I did it with a positive charge and a negative charge, everything would be the same, except as we saw before, the net electric field would be sideways. We had a positive and negative. But it still would get smaller until it goes over here. Okay, this would be a dipole. So I'm going to go back to the one we just did. Why does it do that? Why does it get bigger and smaller? That's the next problem. First of all, let's calculate for two negative charges. You could do two positive charges, it doesn't really matter. Let's calculate what that electric field is. Okay, two negative charges. So we know that the electric field is going to be straight down. And basically, we look these two vectors here, right? That's this one here. I didn't draw them too well. EA, that's this one here, and EB is this one here. And since this is a similar triangle, all the sides are the same, we're going to that means this angle, which is 90 degrees here, it's 60 degrees here and 30 degrees here and 60 here. Together they add up to 90. Okay. So let me just make sure I don't make any mistakes here. I'm looking at my notes. I'm skipping around on my slides, so that's why I got to find out where the next slide is. Okay, so I'm on slide 90 now. Yeah, so I just keep going. Okay. So here we have a positive or a negative and a dipole moment. And of course, let's start again from the beginning. All right. So the electric field due to this guy here is down. The electric field due to this guy here is up. So the net electric field we know already is going to be like this. All right. So for this case, we have positive and negative here. This C would be the right answer. Okay. And what we're going to do is we're going to try to calculate. We're going to try to calculate how this field is dependent on this distance and these distances and these distances. There are three different distances here. First of all, there's a distance we're going to call it y. How far away are you from the dipole? Okay. Now y is going to change and r is going to change as you get further away. And this distance here is the distances between the two charges. We're going to call it A. This is A. This is plus A. This is minus A. So these are both A. Okay. So basically what we have to do here is we have to find one component of this vector here. Okay, find one component because don't forget the net electric field is to the right. These two don't matter. Okay, the y components, they're going to cancel each other out. So we have one operation to do. We know how long this we know how long this is, and we know how long this is. This is how long it is. E1 here equals E2, and it's this long. We're not going to calculate it with numbers here. We just KQ over R squared is the length of these vectors. All right. We're not worried about the y components because they're going to cancel. In other words, the y component of this vector is going to cancel the y component of that vector. And so we don't worry about it. I'm going to erase it. All right. All we need is the x component. And to do the x component, we're going to need a couple of relationships. All right. So again, the x component of E1 will be the same as x component of E2. And it's going to equal to KQ over R squared. So the x component of that is going to equal to E1 cosine of theta. Okay, now what's the cosine of theta? Theta here is the same as theta here. What's the cosine of this angle here? Well, it's adjacent over hypotenuse. So the cosine is equal to adjacent, which is A, over hypotenuse, that's this here. Well, what is that? Well, that's R, but R, we want to know what R is. Now, R is A squared. This is R squared, by the way. I'm going to put it back there. R here is A squared plus Y squared. In other words, A squared plus Y squared equals R squared. Okay? Or R, if we solve this for R, it's the square root of both sides. So it would be A squared plus Y squared, the square root of that. Okay? So let's go back here. What's the x component of this vector if the vector is this long? Well, it'll be that times the cosine of this angle. That's the cosine of this angle here. And the cosine of that angle is adjacent over hypotenuse. We just said the hypotenuse is that, so it's adjacent divided by hypotenuse. KQ over R squared times adjacent divided by the hypotenuse. Okay. Now, what we're going to do, we're going to put in for r squared this. In other words, that's why I had it separated. This is going to be replacing this. All right. So what do we have finally here? We have KQA divided by a squared plus y squared times a squared plus y squared, square root of that, which I have over here. Now this is to the 1 power, and this is to the half power. We know when you multiply numbers in exponential notation, you add the exponents. So this is what I do. 1 plus 1 plus a half is 1.5 or 3/2. So this tells you what the electric field is. All we got to do is multiply it by 2 because we got another same electric field from the bottom charge. So I have this 2 here. So the total electric field, I mean, in other words, the length of this vector is given by that equation. Okay. Here's the interesting thing about it. It's got A here, and Y, which is the distance over here on the numerator. So as we go further away, A stays the same, but Y gets bigger. Okay. So what we're going to do is what happens, let's say we're very far away. That means Y is much bigger than A. If Y is much bigger than A, that means we can forget about A. Okay. For Y bigger than A, we just have Y squared, square root of that times cubed, which is over here. And Y, the square root of Y squared is just Y, and that's cubed. And this is what you saw in the film, that the for the dipole, the electric field drops off as 1 over Y cubed if you're very far away. 1 over Y cubed. It drops off very rapidly. But now, why does it get, as you get closer, it gets bigger, 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 and then it gets smaller, smaller, smaller again? Why does it do that? Well, you can see that almost over here. Oops. What happens is that as you bring this point down, the total, at some point, A is not much bigger than Y. And so what happens is that Y, the A here, at real close distances, makes the total electric field 0. So it starts decreasing again. Now I do have, I guess I don't have it here. So anyway, so this is why he pointed out in the film, the electric field for a dipole drops off as 1 over distance cubed as you get further away. And it approaches 0 as you get over here, because you see when you get to the middle here, the electric field is toward this one, and it's away from the opposite charge. So I know this was some hairy stuff here, but so I'm going to let me turn this off. I'm going to talk about the end of this chapter. This will be finishing off this chapter. And we'll be talking about something called, well, something called Gauss's law. But before we get to that, all the problems we've done up to now, we've talked about point charges. We found the electric field to do 1-point charges, 2-point charges, 3-point charges, etc., etc., etc. And we saw that it's pretty strenuous to calculate all those electric fields. So it's got to be a better way to do this stuff. So imagine that we have not a point charge, We have a shape with a uniform charge distribution. In other words, there's charges here all over the place. We can consider each one of them to be a point charge. That's why we call this little charge, which is part of the total charge here, is delta little q. Okay, and if you, that little charge is a point charge, and if you go over here, there's an electric field. In this case, this is a positively charged surface. A positively charged surface, so electric field is away from the charge. But how do we find the total? If there's more charges here, how do we find that? In other words, this could think it could be made up of many of these charges. Here's another one. Here's another one. Here's another one. We do the same thing. We go to some point and we add up all those charges. Now, this charge here, electric field due to this charge here, is just given by this equation. Don't forget this, I mentioned this before, that this is another way of writing K. And today you're going to see why we use that. Well, maybe not today, but at least next time. Why we sometimes say that electric field is KQ over R squared. And sometimes for K we use a different constant, 1 over 4 pi epsilon naught. So basically what we need to do is start adding up all the other Q's here also to find the electric field here. Each one of them contributes to the electric field. Each one is a certain distance away. Okay, and so we start adding up all the little dq's divided by distance squared, and basically make this number of dq's here infinite. So you know what I'm coming to. This is where calculus comes in. This is so even though we don't do calculus, this is the reason we need calculus. Okay, to calculate the electric field to a uniform charge distribution. That's not a point charge. Right now we did point charges. So let's do, but there's a way to avoid using calculus for some situations. All right, we're going to come back to that. Well, we can avoid using calculus first of all by looking at an example here. This is we want to find the electric field due to a ring of charge whose total charge is q. In other words, this is a ring of charge. It's made up of many point charges. This is one, dq, another dq, 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 and all the dq's add up to that. All right. Now we want to find, let's say, right on the center, a line going through the center of this circle, carrying all these charges. We want to find the electric field here. So let's calculate just to this one charge. Okay, and this is R, this is the radius of our charge circle, and this is how far away we're going from the center. So we're right over here, and we're going to call this electric field dE. All right, for a little electric field due to this dq. So it's just a 1 point charge there. Okay. So first of all, what is dq? What is dE? I'm sorry, dE. Well, it's going to be the regular equation, except the distance from the charge is that distance here, x squared plus r squared, the square root of that. So dE is going to equal to k dq over r squared, and r squared is just this squared, right? Don't forget how we got this. This is a right triangle. This squared plus that squared equals this squared, and therefore this squared will be without the square root here. All right. So again, we're going to basically go around here and adding up all the charges. But if we look at it, what's going to happen here, that this little charge has it in the electric field is that way, has an X component like this and a Y component like that. And first of all, I know if we're going to go around, once we get past here, once we get past here, what will change is that this Y component now will be up. So once we start adding the charges, say we add a charge from here, everything looks the same except this now will be up. That means all the Y components as we go around and add them up are going to cancel. So we're just going to ignore them, right? So we are going to just calculate the X component of this because the Y component is 0, right? This one here, which will be, say, from a charge down here, is going to cancel that one here. And there'll be a charge canceling the Y component from here to here on every piece of this circular ring. So this problem turns out to be quite easy because all we have to do, therefore, is ignore these two and just calculate the X component of this. All right, so let's take a look how we're going to do that. So first of all, what is the length of this? It's this. This is the length of this dE vector. So the X component of that will be dE times the cosine of this angle here. Okay. We look at here, the cosine of this angle here. We know this is that long. So this is going to be equal to that. dE times the cosine of theta. Now what's the cosine of theta? It's adjacent, which is X, over hypotenuse, which is this. So we're going to put in for cosine of theta right over here. All right. I'm going to take this away and put in this, because that's what cosine of theta is. It's adjacent over hypotenuse. Adjacent over hypotenuse. Now, when I multiply this times this, I get x squared plus r squared to the 3/2 power. This is to the 1 power over here. And this is to the 1/2 power. So you add the powers. 1 1/2 is 3/2. And you got an x here and you got an x on the bottom here. All right. So this equation tells you the electric field due to this. Just due to this point charge at this point. Okay, here it is, I just rewrote it. And therefore the total electric field, if I do this to all the charges, is going to be the sum of all these delta x's, DEX. All right. Each one's got everything the same here. So basically all of these are going to add up to, all the DQs are the only thing that's adding up. And you know they add up to what? Q. They add up to this number over here. So instead of putting all the sum here, DQs, we're just going to replace that with Q, capital Q. Because all the DQs are going to add up to capital Q. And this is the electric field, the total electric field, not dE anymore. Along here, the direction of the electric field is going to be to the right, and the magnitude will be this equation here. Now we're going to pull a fast one here. Okay, so what I'm going to do, I'm going to show you, right? So this is the now what we calculated, the electric field at this point, due to all the point charges that make up this ring, is given by this equation, right? Now let's answer a couple of questions. For example, all right, it tells you the electric field at various values of x. Here's x. Here's r. R does not change if we go along here. But what would it be, for example, if, for a couple of examples? What if x was very much bigger than r? In other words, if we went pretty far away so that x here is much bigger than r. Well, let's imagine this. If x is much bigger than r, then it appears that, I mean, let's say you go meters away from here, you wouldn't even be able to see that this is actually a ring. It'll look like a point charge, right? If you go far enough away from it, it'll look like it's a dot. And we know what the electric field away is due to a point charge. Let's see if you get that. So if x is much bigger than r, that means what we can do is neglect r here, just take it away for x much bigger than r. Don't forget, we're doing this x much bigger than r. We can ignore r here, and we'll have x divided by x. Well, first of all, this will be x squared. The square root of that, this will be x cubed on the bottom here, because you have x squared. Take the square root of x squared, which is x, and that's cubed because of this here. So basically, for x greater than r, e, x much greater than r, e is equal to kq over r cubed over x cubed. But you got an x here. And so this x will cancel off one of these x's. This becomes just x squared. And this is the electric field due to a point charge whose charge is just q, because you have kq over distance squared. So basically, looking at these, a maximum and a minimum, and do you get what you expect to get? Yeah, if I go far away from this ring, I can't tell it's a ring. It looks like it's a point charge whose charge is q, and we know for a point charge, it drops off as 1 over distance squared, right? So kq over x squared. What would be the electric field at the center? So at the center, just let x equal 0, right? And the electric field will be x equals 0 here. 0, right? X would be, electric field here would be 0. So as you get closer, the electric field would get bigger because you're getting closer. But if you get too close, because x is here getting smaller and smaller, you have an x on the numerator. And as x approaches 0, actually x becomes 0 here, the electric field will be 0 because x is 0. And so basically you can see the electric field is, for a ring of charge like this, is very similar to a dipole. The electric field gets, as you get closer to the charge, it gets bigger, bigger, bigger. But as you get very close, it starts getting smaller, smaller, and it's 0 at x equals 0. Okay, so it gets bigger as you get close. Bring this point from far away, and then it starts getting smaller again. Okay, so I promised you that I'm going to show you an easier way of getting finding electric field to charge distribution, where you don't have to do, like, this is like pre-calculus here we're doing here, because we're making, sort of dividing up into a lot of little charges dq, and then we're adding them up. So what we're going to be talking about is something called Gauss's law. But let's back up. If there is an electric field anywhere. And let's say there's electric field here going from left to right. It's a constant electric field. And I have here, let's say, a square. Now, besides a square, I could have any figure here, like a circle. And I hold it sort of sideways to the electric field. This vector here, which I call A, is a vector that represents the area of what I'm holding here. It's perpendicular to this square. And the electric field is in the same direction as that square. All right? So we define electric flux as the strength of the electric field times the perpendicular area through which it passes. In other words, if they're set up like this, the electric field, all the electric field passes through the area. But if I tilt this slightly, then the flux gets smaller. Okay, that flux is smaller because that area now, just forget, this is the perpendicular vector to this little square. There's an angle between them, and therefore the flux, the amount of electric field going through this square is less. Matter of fact, it's going to be less by this amount. It's going to equal to EA times the cosine theta. While over here, the electric field was, the flux is just E times A. That's the way it's defined. All the electric field goes through this area. But if this is at an angle, then the flux gets less. The flux through here gets less. So A is the area of the slanted side. A1 is the... Now this is fairly simple concept, not very difficult. And I sort of summarized over here. This is something I would write on the board if I had a board. So that square that I had over here doesn't have to be a square. It could be a circle also. So here's a circle. And I'm going to turn the circle so basically it's facing this electric field. And it'd be nice if I actually had a circle and did that here, right? All the field lines would go right through. But if I tilted it at an angle that not all of the field lines would go through. Most of them would go through, but the flux now, which is EA cosine of the angle between them, is given by this equation. This is the flux of a field through a surface area. And it's very easy to calculate. For example, let's say the area of this circle was 5 square meters, or the area of the square was 5 square meters. And the electric field was 200. I have it over here. And the flux, therefore, would be, if the circle was turned at an angle of 60 degrees relative to the electric field. Don't forget, this is A, the vector A, and this is the electric field. If the angle between them was 60 degrees, then the flux would be EA cosine theta, EA cosine of 60, which would be 500 newtons per meter squared. Okay, let's do a couple more examples. So here we have a square. The vector representing the area of the square is perpendicular to this. So the angle between them is 90 degrees between the electric field. This is electric field, and this is the area. And so basically what we're saying is the angle between the flux, there's no electric field lines going through this square. So the flux is 0. And to calculate the flux, you say EA cosine of 90 degrees, that's 0. So the flux is 0. Let's do, right, so the flux would be 0 over here. Let's assume that the electric field is up, and the area is up also. So now basically the angle between these two is 0. So now we say that the electric EA is equal to the flux, because the cosine of the angle is 0. Cosine of 0 is 1. But if there's some other angle, like over here, the electric field was here and the area was straight up, then this would be the angle between them, and we say the the flux through it now would be EA times cosine of. So that's what we define, the way we define flux. And let's do an example here. So we have here a rectangle, length and width. So we know the area of this rectangle, length times width. I'm not going to write it down here, just write equals length times width. So the normal vector makes an angle of 35 degrees with the vector describing the direction of the applied field. So this box, I can't turn it here because I don't have 3 dimensions, is turned slightly relative to the electric field. So there's an angle between the area vector, which is sort of perpendicular coming straight out, and the electric field. So what is the flux? So basically this is what you're using. You say the flux is E times A. E is just the electric field. A is a vector representing the area and the angle between the two vectors. Okay, so here the angle is 35 degrees. E is 52,000. Length and width, which will give you the area over here. Just looking at my notes here. Okay, so the calculations, if you do that, here it is, here's the calculations. 5,000, 52,000 times 35 times 7.75 times the cosine of 35 degrees gives you this answer. So let me just do one more slide, and we're going to finish this up next time, because this is what we're going to look at is using this material is called Gauss's law. We know that due to a point charge, don't forget, a point charge versus what we were doing just now, those things were not point charges, but they were close to it. They were not point charges. We know that a certain distance away, there's an electric field given by this equation here. And you may have seen it as KQ over R squared. What we're going to do is, here's the point charge. This is a point charge. And what we're going to do is we're going to draw an imaginary surface around the point charge. This is 3 dimensions, so this surface is not a circle, it's like a bowling ball. And the charge is in the center of the bowling ball. Or it's a basketball, and there's a charge in the center. All right? And this electric field is coming out in all directions. So we're looking at just one point here on the surface of the charge. We're going to call area as dA, and the electric field due to this Q is just E, not dE. It's E because this is all there is. There's nothing else. One charge. Now we know that the area of a bowling ball is not pi r squared. It's 4 pi r squared. Okay, so we're going to use this equation that the flux through here, which is E times A, there's no cosine theta, so it's just E times A. Okay, because both E and A are in the same direction. So all we got to do is to plug in for A what the area is of this ball that's circulating this Q. And that's, if we solve, it's 4 pi r squared. So we're going to put that in for E over here. We know that E due to a point charge is 1 over 4 pi epsilon squared times Q over R squared. That's E. right? That's E to discharge. We know that. We just did many problems like that. All we got to do is multiply this by this. And look what happens. First of all, the pi's cancel here. Well, we can solve this for the flux is just Q over epsilon naught. This cancels off. The R's cancel off. So the flux through this surface is just Q divided by epsilon naught. Now this is generally true. But this is one of the reasons that epsilon naught is used over here instead of K. Because of this, the 4 pi's cancel off. And the flux through a surface like this is Q over epsilon naught. It turns out that this equation, what I just did, is, I'll tell you the next slide what it is. Okay, it's good for any surface under certain conditions. That the flux through any surface is equal to the charge inside the surface divided by epsilon naught. Okay, the flux through any surface is equal to the charge enclosed by the surface. That means inside the surface. In this case, we just Q divided by epsilon naught. So what that means is that if we can do this, we don't have to use calculus here to figure this out. But what we need to do is, one of the things we needed to do here was to know what the area of that surface is that we enclosed it in. It was a ball. I mean, the area is 4 pi r squared. If it's not a ball, then maybe it's something else whose area we can find. We know the formula. So in order to use this Gauss's law, first of all, the charge must be at the center of some Gaussian surface. Like that, the Gaussian surface in this case was the center of a ball, but it doesn't have to be a ball. Any Gaussian surface would be good, as long as you know the flux through that Gaussian surface. And that flux through the Gaussian surface has to be constant, right? The electric field must be perpendicular everywhere on the Gaussian surface, like it was here. The magnitude of the electric field must be constant at the surface. In other words, if we go, say, over here, the electric field has to be the same as it was over here. Anywhere on the surface, it's the same. And we must be able to figure out the flux through the surface. And that's easy to do if you know the equation for the area of this. In this case, the Gaussian surface was a ball. But the couple of examples we're going to do next class will be a couple of other Gaussian surfaces where you can avoid this integration because you know the area of the Gaussian surface, of the flux through the Gaussian surface. All right, so that's where we're going to end today. Let me go back to, oops. And let's see. I need to stop recording. Let me stop sharing first of all. And then stop recording. Let's see how I stop recording. I already forgot how to stop recording. Oh yeah, over here.